Hello students, welcome to EPG Pathshala. Today we shall be talking about atmosphere, ocean and climate dynamics of the paper atmospheric processes. As you all know, atmosphere and ocean, they are the two most important components of the earth system that are highly mobile. The fluid properties of air and water of these two entities set up spectacular examples of dynamics that we are generally unable to reproduce in a laboratory within a confined area. So, the most important factor that distinguishes the atmosphere and ocean compared to a fluid in a flask is the vast amount of their size and extent. Moreover, the spherical shape of the earth and its rotatory frame of reference, that is one complete rotation per day, it adds more complexities in the dynamics of atmosphere and ocean. In addition to that, the differential heating experiencing from the sun, that means strong heating in the tropics, mild heating in the mid latitudes and very less heating in the polar regions, sets up thermal gradients in the atmosphere and oceans and causes various forms of dynamics. Climate, on the other hand, is a name we associate to the long term mean behavior of the atmosphere and ocean that we see around. The interaction of the atmosphere and the ocean along with the land, biosphere and solid earth and the exchange of matter and properties between them makes the long term state of our earth system, which we call as climate systems. For this reason, the dynamics of the atmosphere and ocean become an integral part of the climate evolution. So, this module will lead us to some of the interesting aspects of the dynamics of atmosphere and ocean and will enable us to comprehend and answer some of the features of atmospheric and oceanic circulation that you usually confront in our day to day life. So, this module will describe about the following key points: the physical properties of the atmosphere and ocean, various forcing experiences over the atmosphere and ocean, the dynamics of atmosphere and ocean and atmosphere as a part of climate system. Besides, we will also do brief history on climate change. So, as you all know, atmosphere is the envelope of air surrounding the earth and held closely to the earth's surface by the gravitational forces. The atmosphere, it extends vertically from the surface of the earth up to about a maximum of 100 miles. The density of air at sea level is nearly 1.225 kilograms per meter cube at 15 degrees Celsius and it decreases rapidly with height even at 100 miles. It is less than that of the best vacuum available in the laboratory. Thermally, the atmosphere has been divided into 4 layers and they are, the first being troposphere from an altitude of surface to 10 kilometers on an average, stratosphere from 10 to 50 kilometers, mesosphere from 50 to 80 kilometers and thermosphere from 80 kilometers and aloft. So, the troposphere is the lowest part of the atmosphere with near linear decrease of temperature with height, that means from 273 kelvins to 220 Kelvin. The end of troposphere is called as tropopause, which is usually at a 10 kilometer above sea level, where the aeroplanes cruise. The linear decrease of temperature with height in the troposphere is due to the radiative cooling of the atmosphere from surface to aloft. In the stratosphere, the temperature increases with height from 200 kelvins to about 300 kelvins. This is due to the presence of ozone molecules in this layer, which absorbs the downwelling ultraviolet radiations from the sun and heats the air there. The cooler tropopause and warmer stratosphere makes this part of the atmosphere very stable with warm stratospheric air over cold tropospheric air, and so the name stratosphere. The upper part of the stratosphere is called as stratopause. The height above stratosphere is called mesosphere, where temperature again falls with height as it cools by radiation. The height between tropopause and about 100 kilometers is often called as middle atmosphere. The vertical profile of atmospheric temperature, that means from surface to about 70 kilometers altitude, is approximated as P is equal to PAE minus Gz by RTC. Here PA is E raised to the power minus Z by Hs, where Hs is the scale height defined as RTC by G. Here R is the universal gas constant, Tc is the temperature of 250 Kelvin and g is the gravity of the earth. Atmosphere is forced by the differential solar radiation with nearly 300 watts per meter square in the tropics, within, that means plus minus 223 degrees north south with respect to the equator, and nearly 50 watts per meter square in the polar region. The outgoing radiation, that means the combination of sensible heat, latent heat and long wave, is nearly 250 watts per meter square in the tropics. The result is a net heating at the tropical atmosphere and cooling at higher latitudes. This gradient heating from the sun is the major driver for most of the large scale dynamics and general circulation in the atmosphere. Now coming to oceans, as you all know, the 70% of our Earth's surface is covered with oceans. The average depth of the ocean is nearly 4,000 meters. Ocean is the largest storage of water in the Earth system. The atmosphere holds only 0.03 meters of water if it all precipitates uniformly over the entire global ocean. The Antarctic ice sheets is the second largest storage of water. If it all melts, it will add 76 meters of water over the entire global ocean. The river and other forms of water storage add up to just 4 meters of water over the ocean. Thus, oceans by all means are the largest reservoir of water in the earth. The ocean temperature generally decreases with depth. The first few meters of the surface ocean, that means nearly about upper 50 to 100 meters, are well mixed, and properties such as temperatures, saltiness or salinity and other nutrients are quite uniform over this depth. This is called as the mixed layer of the ocean. Below the mixed layer and up to nearly 200 to 500 meters, the temperature decreases sharply. The most part of the heat stored in the ocean are above this depth. The region of sharp gradient of temperature with depth is called as thermocline of the ocean. Further, the composition of ocean water is nearly constant with iron mass ratio of chloride 55%, sodium 30%, sulphate 8%, magnesium 4%, potassium 1% and calcium 1%, so that the state of the ocean water can be described by just one major concentration called salinity. It is usually expressed as the amount of salt in grams per kilogram of sea water. The average salinity of global ocean is 35 parts per 1000. The ocean is heated from the surface, unlike the atmosphere which is heated from below. The surface heating makes the ocean temperature larger at the surface and decreases gradually with depth. This is a stable condition, that means when warm surface water resides over the cold subsurface water. Therefore, enormous amount of mechanical energy and thermal cooling is required to mix or stir up the surface ocean. Just like the atmosphere, the ocean is also affected by the differential heating from the sun. The tropical oceans are generally warmer and more stratified in vertical than the mid and high latitude oceans. The oceans gain heat in the tropics and transport them to polar regions where the heat mediates to the atmosphere. The large scale air sea exchange of heat is therefore tend to level the thermal gradient in the atmosphere and ocean, which results in large scale general circulation. So, let us now discuss briefly about climate. It is the long term average of day to day state of the atmosphere and ocean or any such element of our earth system. Since the formation of the earth, that is believed to be some 4.6 billion years ago, the climate is under gradual modification. Due to the reduced radiation pressure in the sun's core and reduced nuclear fission, the sun was 30% less luminous during the early evolution of the earth than what it is today. It is a puzzling question what kept the earth's atmosphere warm with a 30% fainted sun in the beginning. It is believed that the amount of greenhouse gases in the early atmosphere must have been extremely high. For example, CO2 concentration was nearly 20,000 times higher than that of today. This helped the atmosphere to remain warm and support the early form of microbial life even 3.0 billion years ago. The early atmosphere was highly composed of reduced volcanic rocks. The oxygen was extremely low at that time. It is believed that the long term carbonate silicate geochemical weathering of rocks, increased photosynthesis and gradual development of a brighter sun all have played intermittent roles to bring the climate amenable for human life as we see today. Modern climate has an average atmospheric surface air temperature of 15 degrees Celsius. In addition, because of the tilt in the Earth's axis of rotation, the solar radiation arrives at southern and northern hemisphere is asymmetric, and that causes seasons. Now, coming to the fundamental of dynamics, which is the core of this module. The fundamental laws that govern the dynamics of atmosphere and ocean follow closely the Newtonian classical mechanisms. Simply, the differential heating of the atmosphere causes gradient in the horizontal thermal structure, which in turn causes a pressure gradient, because the temperature, pressure and density of the fluid are thermodynamically connected. This pressure gradient drives the air and water down the pressure gradient. The heating of the atmosphere from the bottom causes air to be less stable and forces convection. The large reserve of potential energy by the gravitational force and thermodynamics, that means the internal energy, could be released by chaotic interaction between the perturbations and the mean flow. All these causes the dynamics in the atmosphere and ocean. To understand this, one should ask a question: what is the difference between the dynamics, that means motion, of an ordinary fluid in a laboratory and the fluid that we see in the atmosphere and ocean? So, this table summarizes the differences between them. So, the properties that distinguish between laboratory fluids and planetary fluids are spatial scale, time scale, size, frame of reference and surface. On a scale spatially, the laboratory fluids, they range from 1 to 100 meters, while the planetary fluids will be from maybe 10,000 to lakhs of kilometers. The time scale varies from 1 to 100 minutes for laboratory fluids, while it may be from 10 to 10,000 days for planetary fluids. Further, the size also varies from few grams to kilograms in laboratory fluids and from 1000 kilograms to maybe various kilograms in planetary fluids. The frame of reference is stationary for a laboratory fluid, while it is rotatory for a planetary fluid. Also, the surface is plane for laboratory fluid, while it is spherical for planetary fluids. Because of these differences, exciting and unfamiliar to laboratory fluids features of dynamics set up in the atmosphere and ocean that we generally call as geophysical fluid dynamics. For a thorough and detailed discussion on the complexities of geophysical fluid dynamics, the students are encouraged to read the books by Pidioski and Gill. Now, coming to the conservation of mass and momentum, the conservation of mass follows the basic Newtonian principle that the total mass of the fluid remains constant unless it is supplied through external source or consumed or transformed internally and changes its form. Consider a fluid volume of the shape of a cube. The total change of mass inside the box is equal to the net rate of mass that is entering or leaving the box through all the sides. The net balance of the fluid mass can be written as shown in the equation 2. Here, rho is the density of the fluid and u is the velocity. With sufficient approximation, the density can be assumed to be constant over a long time. Moreover, the fluid can be assumed as incompressible. This approximation is good with the ocean. In the case of atmosphere, considering the decrease in density with height and assuming the atmosphere is dry, this quantity is rather conserved, where T is the temperature. With this assumption, the conservation mass represents the equation of continuity, which is whose expansion in 3-dimensional Cartesian coordinate translates into where u, v, w are velocities in x, y and z directions respectively. The conservation of momentum assumes the Newton's second law of motion for the fluid. The net forces experiencing on a hypothetical fluid volume will result in the net acceleration of that fluid volume. In the case of laboratory fluids, this is represented by the famous Navier-Stokes equation, and in the case of planetary fluids, a few additional forces come into picture by virtue of rotating frame of reference and curvature of the surface of the earth. One such force is the Coriolis force. It is a fictitious force experiencing over a moving body in a rotational frame of reference. Earth is a rotating frame with a period of rotation equal to 1 day, which imparts an angular velocity omega of 7.29 into 10 to the power minus 4 per seconds. Because the earth rotates from west to east, the tendency of Coriolis force in the northern hemisphere is to rotate or steer a moving body to its right, and vice versa in the southern hemisphere. The intensity of the Coriolis force is maximum at the poles and 0 at the equator. The equation for motion of planetary fluids can be summarized as given in the equation 3. Here u is the total velocity, f is the geopotential defined by the sum of gravitational potential and centrifugal potential of the earth rotation. For the vertical axis pointing outwards along the radius of the earth, the geopotential is equal to the gravitational force of earth. This term is approximated as to be the hydrostatic assumption with a differential of P by Z. This second term on the right hand side is the pressure gradient force. The third term is the Coriolis force. The fourth term stands for the kinematic friction and viscosities of the fluid. In the large scale planetary dynamics, they represent eddy viscosity, with each eddy standing for irregular chunks of fluid analogous to a molecule in the molecular velocity, but with extremely high mass and viscosity. Now, coming to potential vorticity, although the momentum and so do the angular momentum of the planetary or geophysical fluids are conservative in nature, because of the rotation of the earth, a virtual element of force comes into picture, that is Coriolis force, which often exchanges the momentum between the rotational part of the motion and the planetary rotation of the fluid inherent from the rotation of the frame of reference. In such a situation, a more relevant and conservative property of fluid dynamics called as vorticity can be defined. Due to the shear in the fluid motion, the fluid elements can rotate relatively to its neighbor. This is called as the relative vorticity, usually measured by the shear of the flow. The equation of relative vorticity is where u is the total velocity. The total vorticity, which is a vector measure of rotation, is 2 times that of local angular velocity. So, as you can see in this figure, in the first figure, the relative vorticity is demonstrated as a scalar measure of rotation, and it is equal to 2 omega. In the second figure, any plane on the surface of the earth is under the rotation by virtue of earth rotation. The magnitude of rotation is omega sin theta, where theta is the latitude. The planetary rotation of vorticity is given by 2 omega sin theta, where theta is the latitude, as I told you. The additional source of rotation comes from the gradient in the stratification of fluid across a broader horizontal distance. Because of differential heating and compositional changes of fluids in the atmosphere and ocean over a larger distance, the isobars, that means the lines of constant pressure, and isopycnial, that means the lines of constant density, are not parallel. In this case, the fluid has a tendency to make these two isolines parallel, which offers a tendency of rotation. Because there are various tendencies to offer rotation or vorticity in a fluid, in the geophysical fluid dynamics, a more conserved quantity can be arrived, which is known as potential vorticity. This potential vorticity of the fluid parcel is retained over a longer period of time and space scale, which offers a greater predictive value in geophysical fluid dynamics. This figure shows the isolines of pressure and density, and they are not parallel. This offers a tendency in the fluid to rotate in such a way that the isolines become parallel. This is called as baroclinic vorticity. Now, coming to the dynamics of the atmosphere and ocean. In the above section, we introduced a few governing rules that are handy to describe the dynamics of the atmosphere and ocean. However, one should bear in mind that the solutions of geophysical fluid dynamics problems are rather intuition driven. That means, when we explain a typical feature of the dynamics, we only consider the most possible and necessary terms in the equation of motion, while others are neglected. So, coming to geostrophic and quasi-geostrophic dynamics. The geostrophic dynamics is obtained just by equating two terms in the equation of motion. It is basically the balance between the pressure gradient terms and Coriolis force. In the two dimensional and horizontal cases, this can be written in component form as shown in equation 5. Here u and v are the zonal and meridional velocities, and p is the large scale pressure over extremely larger distances. Geostrophic currents are time independent or degenerative in nature, meaning that if you know the pressure pattern, then velocities, that means of ocean currents or atmospheric winds, can be readily deduced from it. Since there is no time dependent term, it cannot provide any information about the future of the currents. A close examination of above equation tells us that the currents are parallel to the contours of pressure as shown in the next slide. The geostrophic currents are time independent or degenerative in nature, meaning if you know the pressure pattern, then velocities of ocean currents or atmospheric winds can be readily deduced from it. As you can see in this figure, the isobars and current or wind vectors in a pure geostrophic balance in the northern hemisphere. That is why we are saying the currents are parallel to the contours of pressure as shown in this figure. Now, most of the mid latitude atmospheric circulations are pressure pattern driven and geostrophic relation that gives great amount of accuracy about the deduced winds. However, in tropical regions, the dynamics are not purely pressure pattern driven, but convection plays an important role, and therefore, geostrophic relations are not very valid. In addition to that, the Coriolis force, which is central to the geostrophic dynamics, is weaker in the tropics because of the proximity of the equator. As we already discussed, that Coriolis force is proportional to sin theta. Hence, the tropical dynamics are seldom deduced from geostrophic relations alone. Although the geostrophic relation gives great accuracy in deducing currents or wind from pressure patterns, the geostrophic relation is degenerative in nature, meaning that it has zero predictive value because it is time independent. Adding a time component to geostrophic relations will give a predictive value to it. This is called quasi-geostrophic dynamics. This dynamics starts with the basic assumption that atmospheric or oceanic dynamics are not purely geostrophic, but it has a slight deviation from the geostrophy. The deviations of currents from geostrophic relations are taken as u is equal to u naught plus E u1, where u naught is the pure geostrophic velocity, E is a small coefficient representing an impurity in the geostrophic velocities. The quantity E is called the Rossby number, which is defined as E is equal to u by Fl, where u is the advection velocity scale, F is the local Coriolis component, and L is the advection length scale. For large L and small u, Rossby number is small, that means often from 0.1 to 0.01. With this approximation, the tendency of velocity, that is expressed in terms of stream function, can be written as shown in the equation 6, where psi is the stream function, j is the Jacobian parameter, f is the Coriolis parameter, eta b is the ambient potential velocity of the local latitude and its variability due to curvature. The term is another representation of the potential vorticity, remembering from previous section that it is a conserved quantity throughout the fluid dynamics. Now, coming to planetary wave dynamics. The solution to the above equation can be obtained by assuming a general wave solution of the form where k is the wave number in the east west direction of the earth and omega is the frequency of the wave. Substituting this into the above equation gives a rich spectrum of waves. These are called the planetary waves, which always dominate the atmospheric and oceanic dynamics. Away from the tropics, the planetary waves are generally called as Rossby waves. They always travel westward. Their horizontal extents are thousands of kilometers. Close to the equator and tropics, the planetary wave solutions become discrete in nature, so that only a definite number of modes of waves exist, that means either symmetrical or antisymmetrical with respect to the equator. They can be represented in a wave number frequency diagram as depicted in the figure 5. As you can see in this figure, it shows the train of Rossby waves in the Atlantic in a quasi-geostrophic model simulation. A pair of red and blue circles shows one Rossby wave, with red indicating positive stream function and blue indicating negative stream function. The next figure shows the dispersion curves of various possible planetary waves in the tropical region. The eastward and westward wave numbers in x axis, that means k is equal to 2 pi by L, and frequency in y axis, that means omega is equal to 2 pi by T. Here T is the time period. The next figure, it shows us the three-dimensional schematics of 1 Kelvin wave and a half of an equatorially symmetric Rossby wave in the ocean. The interface of the ocean tentatively represents the thermocline, where the vertical temperature gradient is the largest. Thermocline is usually within 150 to 200 meters in the tropical ocean. It dips or shoals according to the sign of Kelvin Rossby. After this, in the next figure, we can see the plan view of one equatorial Kelvin wave and a pair of Rossby waves in the ocean. The H and L in this diagram stand for the high and the low sea surface height or pressure pattern. Now coming to thermal winds, it is observed that mid-latitude westerly winds, that means winds coming from the west, are stronger and of jet-like shape as we move upward in the troposphere. These are generated due to the thermal gradient in the lower atmosphere and hence the name thermal winds. When combining the geostrophic equation with the hydrostatic equation, that as we discussed earlier, one gets the following two equations as shown in 7 and 8. Here the zonal and meridional gradients of the density of air can be replaced with sufficient approximation by the temperature, and one can obtain equations 9 and 10. These equations show that as the temperature has a gradient in y direction, that means meridional temperature gradient, the zonal, that means east-west winds, increase with height. This relation is called the thermal wind. From tropics to polar regions, as the temperature decreases, the upper atmospheric winds are observed to be strongly westerlies, that is blowing in the eastward direction. This phenomena is explained with the thermal wind as shown in next figure. So, this figure shows the mean meridional cross section of wind and temperature for January and July. The thin solid temperature lines are in degrees Celsius and dashed wind speed lines are in meters per second. Now, we have an important concept of Ekman transport. When wind blows over the earth's surface, a stress is exerted on the surface, whether the surface is solid earth or sea. In the case of ocean, this stress exerts a motion in the surface layer where it is in contact with the wind stress. This is called as Ekman transport. In this case, we consider a balance between Coriolis force and the wind stress and its penetration with depth in the fluid medium as shown in the equation 11 and 12. Here, x and y are the wind stress experiencing over the surface ocean in x and y direction. F is the local Coriolis parameter. U and V are the zonal and meridional ocean currents. The penetration of wind stress is typically up to upper 50 meters in the ocean. The resulting circulations are UE is equal to Y upon gamma F and VE is equal to X upon rho F, where UE and VE are the depth integrated from surface to depth at which the wind stress effect vanishes the currents. The solutions to this equation are sinusoidal functions of depth. That means the current has deflection from the direction of wind axis to the right in the northern hemisphere and it rotates with depth as a spiral. This is called as Ekman spiral. The net averaged over the depth direction of the Ekman currents will be nearly perpendicular to the right hand side of the wind direction in northern or the southern hemisphere. This figure shows the steering of upper ocean currents to the right direction of the wind forcing at the surface. The depth at which the current entirely reverses from that of the surface is called as the Ekman depth. Now coming to ocean gyre circulations. The ocean dynamics is established by the action of wind over the ocean. The large scale surface winds are westward in the tropics because of the trade winds and eastward in the subtropics to mid latitude because of the westerlies. The Ekman transport associated with these winds pushes the water in the surface and piles them up in the center to the wind directions. This causes a pressure gradient and geostrophic current surrounding to the center. The net result is a large scale gyre circulation in the ocean. The solution to gyre circulation is obtained by Sverdrup theory. Consider the pressure gradient, Coriolis force and wind stress forms in the balance equation shown in equation 13 and 14. First, take the vertical integral of this equation, then taking the curl, that is of the two equations, that is derivative with respect to y of the first equation and subtract the derivative with respect to x of second equation, one arrives at equation 15. The above equation means that the net north-south transport V in a gyre is a function of curl of the wind stress. The Sverdrup equation simplifies and relates the ocean gyre circulation to the curl of the local wind stress. However, it clearly does not depict the observed flow pattern for a gyre circulation. It has broad eastern boundary stream functions indicating a broad and weak southward eastern boundary current and tightly packed western boundary stream functions indicating a narrow and strong northern western boundary current. With sufficient modification to this theory and by introducing coastal boundary friction of Laplacian type or biharmonic type as given by Stormet or Monk theory, one can achieve a solution to the westward intensification of boundary currents. The explanation of gyre circulation and western boundary currents intensification can be given by the principle of conservation of potential vorticity. As water travels from higher latitude to lower latitude, the planetary vorticity of it decreases, which is a function of sin theta, but the boundary friction at the eastern boundary contributes a slight shear in the flow in the direction of local planetary vorticity and compensates the reduction in F. Further, the flow from north to south tends to have a positive vorticity, that means rotation tendency in the direction of planetary vorticity, and thus the stream functions of the east becomes broad and stretched. On the other hand, at the western boundary, this boundary friction offers a shear in positive vorticity direction, that means with respect to planetary rotation. In addition, F also increases as water flows northwards. Thus, in order to keep the total vorticity conserved, the water has to steer strongly clockwise, that means gain negative vorticity right after the boundary shear. This causes intense, narrow, sheared western boundary currents, that means orange arrows as shown in the figure. As you can see, this figure is the same as previous figure, but with boundary friction indication by straight arrows of sheared ocean currents. So, now finally coming to ocean atmospheric interactions and climate dynamics. Ocean and atmosphere always exchange mass and momentum, which is the key part of climate dynamics. Such large scale exchanges are central to the process, such as El Nino and southern oscillations. The intrinsic dynamics of the ocean and atmosphere, as we have seen in the previous sections, they are key elements in the large scale dynamics of climate. The large scale and differential heating from the sun warms the atmosphere by the greenhouse effect. This differential heating sets up the circulations in the atmosphere. Once the atmosphere is in motion, it forces the underlying ocean and induces ocean currents. The differential heating received from the sun causes the ocean to transport heat from tropics to mid latitude and release to atmosphere there. This tends to force the atmosphere further there. The precipitation in the tropics and evaporation in the mid latitudes exchange large amount of water between ocean and atmosphere, and it affects the oceanic mixing and dynamics. It takes very long time, that means of the order of thousands of years, for all these processes of interaction and exchange to bring equilibrium and mean state of our climate. Further details can be studied from CUMP 2010. So, dear students, to summarize, on the whole, the atmosphere and ocean exhibit spectacular properties of dynamics due to its large size, its rotating frame of reference and gradient heating from the sun. The dynamics of ocean and atmosphere are integral part of the climate system and its evolution. The steady state balance in the atmosphere, ocean and climate evolutions are indeed the outcome of the intricate connections between their dynamics and exchange of properties between them. Hope you all have learned something from it. Thank you.